Welcome back. Today we're going to continue section 12.2 talking about transforming to achieve linearity. So where we left off yesterday, we looked at two different ways to deal with power models. And then I did highlight that we are going to start talking about logarithms. So basically, anytime you see a curved relationship, that does not necessarily mean that it's a power model. Some of them have a slightly different shape, but they're still curved and can be described as a logarithmic model. That looks like this: y equals a plus b times log x, where a and b are constants. Now, sometimes the relationship between x and y is based on repeated multiplication by a constant factor. That is, each time x increases by 1 unit, y is multiplied by b. That's an exponential model of the form y equals a times b to the power of x, which describes multiplicative growth. So let's take a look at an example here. Let's say that I invest $100 in a savings account that earns 6% interest compounded annually. So after 1 year, I've made $6 interest, and my new account balance is that 100 plus that calculation to get the $6, which is $106, which I could rewrite as this. Or, more simply, 100 times 1.06. So, I can multiply by 1.06 to get the new balance. Now, if I leave that money in for the second year, I would earn 6% in the first year, and then I would get to multiply by 1.06 for the second year, which I could write that as 100 times 1.06 squared and get 112.36. Notice that in that second year I got $6.36 interest compared to the first year's $6. That's because I'm earning a little extra interest because there's a little bit more money that I get to earn interest on. So an equation I could write to model this, and hopefully you remember exponential growth from past math classes, but that looks like this: y equals 100 times 1.06x. Now, here is a table that shows the beginning balance and then the account balance after X years. Okay, and here it is all the way out to, like 100 years. All right, and you can see that this curve right here is not a power model like we looked at in the previous lesson, but this is an exponential model. This represents exponential growth. All right, so basically, if a model of the form y equals a times bx describes a relationship, you can actually use logarithms to transform the data to make a linear relationship. And here's kind of how the math works. If you take an exponential model of this form, you can take the logarithm of both sides. You can then use this property of logarithms to break this up into two different logarithms. You can then use this property of logarithms to bring this exponent out in front and say it's x times log of b. And this equation, actually, if you look at the final equation we have here, log a is just log of a number, which will give you some value here. Log b is a constant, so it's just log of a number. So you'll get just a number here. This is your variable x, and then this will be the logarithm of your variable y. So because log a and log b are constants, we basically have a linear model relating your explanatory variable x to your transformed variable log of y. And you can think of this as like the y-intercept, and this is like the slope because it's the coefficient of x. So if the relationship between two variables is an exponential model, we can plot the logarithm of y, and the base that you can choose to use, you should choose either 10 or e because those buttons are on our calculator. Technically you could choose any base though, but if you do the log of y compared to x, you should observe a straight line pattern in the transformed data. And then you can fit a least squares regression line to that transformed data, and you can find the predicted value of the log of y for any value of x by substituting that x into the equation. to obtain the corresponding prediction for the response variable, you have to undo the logarithm and return it to your original units. And you can do that by using the definition of a logarithm, which is this. If log base b of a is x, then, and the way I teach this is if you have log base b of a equals x, that means b to the power of x equals a. I kind of swirl it. So this base to that power equals that. B to the x equals a is a way you can rewrite that. So for example, if I tell you log of y equals 2, okay, this means log base 10 if there's no base written, which means this means 10 to the power of 2 equals y. And you can write it as 10 to the power of 2 equals y, which is 100. If I were using the letter, a base of e, instead of writing log base e, we write ln. ln of y equals 2, that means log base e of y equals 2, and you can rewrite that as e to the power of 2 equals y. You should also notice, though, on your calculator you have buttons for this. You have this log button right here, and you have the ln button right here. Okay, but one thing I want you to notice here is to type 10 to the power of 2. You can see up above that log button there's a 10 to the power of x, so I can actually press second log to get 10 to the power of, and then I can type 2 to get 100. Same thing down here for ln. If I press second ln, that gives me e to the power of, and then I can type 2, and there's my answer for y. So you can see here that on our graphing calculators you can undo the logarithm by doing the second function key and then pressing log or ln. Alright, so let's take a look at how this works with an example. So let's look at Moore's Law and computer chips. Gordon Moore was one of the founders of the Intel Corporation. He predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. And this is Moore's Law. It's a way to measure the revolution in computing, basically the speed at which we can improve technology, doubles basically every 18 months. So here is some information on some processors, the year they came out, and the number of transistors. Basically, the more transistors, the faster they can go. And you can see this definitely curved relationship here. So, question A. So let's look at, since this is a curved relationship, what we're going to do is we're going to look at a scatter plot of the natural logarithm, that is log base e, or ln, of the number of transistors on a computer chip compared to years. So basically, we're going to compare the date, here the year, to the ln of this number, the log base e of this number. Alright, so when you do that, you get this scatter plot right here. So here's years since 1970, so instead of using these big numbers here, we just basically said the years since 1970, so this would be a 1 and a 2 and a 4 and so on. And then on the y-axis we have, you can see ln of the number of transistors. Now, based on this graph, explain why would it be reasonable to use an exponential model to describe the relationship between the number of transistors and years since 1990. So basically, all we are looking for is this to be roughly linear. So if an exponential model describes the relationship between two variables x and y, then we expect a scatter plot of x comma ln of y to be roughly linear. And this scatter plot of ln of transistors versus years since 1970 has a fairly linear pattern, especially in the first 30 years it's very linear. You can see there's a slight little bump there, but overall there's a very linear trend here in this graph. So that's why an exponential model would be appropriate. Now, there's a Minitab output here of the linear regression of the transform data. Give the equation of the least squares regression line. Okay, and be sure to define any variables. So here's the regression on these two variables here, years since 1970 and ln of transistors. Basically what you're going to do is, just like we write the linear, the least squares regression line for a linear relationship, It's the same idea. We use these two numbers. This is, you know, like the slope of y-intercept. So I plug in the y-intercept here, and then plus, and then the slope times x. And x is the year since 1970. But notice that my y variable here is not just transistors, it's ln of transistors. And of course, these are predictions here for this variable, so it's ln of transistors hat, big old hat. You could also write it like this, but if you write it like this, you do have to define what x and y are, or you could write it like this where the words are actually inside your equation. Alright, now use this model from part B to predict the number of transistors in 2020. So, what I'm going to do is I'm going to just plug in the number of years since 1970. 2020 would be 50 years later, so I plug in a 50 right here. So, I plug in a 50 right there, and I get that plus that equals 25.3562. Now, that's not my final answer. That's my answer for the ln of transistors. So basically all I need to do, and basically I don't really have to know the definition of a logarithm, all I have to know is I've got ln here, so I'm going to do the opposite of ln, which is second ln of this number right here, 25.3562, and I get that number right there. Notice E11 means times 10 to the 11th. And that uses this definition of a logarithm to rewrite it in log form, but that's what you get. That's all you have to type into your calculator, and there's my answer. All right, next. A residual plot for the linear regression is shown below. So we didn't really check our residual plot, and when we look at this residual plot, we might notice something a little concerning. You can see that at the beginning here, it looks pretty good. It's randomly scattered above and below, but then after that, we've got this weird kind of shape to it. So what does this graph tell us about the appropriateness of the model? So it shows a pattern with the residuals going from positive, so here they're slightly positive, and then to pretty negative, and then to positive as we move from left to right. Now, if you look at these numbers, though, the residuals are small compared to the transformed y values. Also, the scatter plot, if you look back at the scatter plot right here, this one, you can see that is much more linear than the original scatter plot. So basically, one thing we're going to look at is this is not even close to linear at all, and this is fairly close. So even though we don't love that there's a pattern here, we should feel reasonably comfortable using this model to make predictions about the number of transistors on a computer chip. Alright, so quick little summary here of what we've done so far. In the first lesson of 12.2, we looked at how to transform a power model, and we could either do that to x, raise that to the power of p, and if that's linear, then we've got a power model, or we could do the pth root of y. And then we just looked at doing an exponential model today, and that would be comparing x to the log of y if that's linear, or we could use ln, so x to ln of y. And then tomorrow what we're going to do in our last lesson of chapter 12 and last new lesson of the year is we're going to look at another way tomorrow to do a power model that also uses logarithms. But for now, that's where we're at. So if you got any questions, please let me know.